Here, this term is equal to 0 because for white noise, there is no correlation between each other. Because the rate p over square root n is larger than the rate so this term is dominant term. Now we can plug in the rate for this one and the rate of this one into this to get the rate for perturbation. The reason I do in this way is because I want to compare these two rates. Since by our assumption that this term is little o1, so the second term is dominant the first term. For some large p and n. After we got the rate for the difference between the sample version of L and the population version, we can analyze the rate under two different scenarios. One scenario is weak cross dependence between F and the white noise. Second is strong cross dependence. First case is kappa max is of a little o factor strings, which means the cross dependence is weak. we copy from the previous page and do some modification. We divide and multiple same term. Since this term is small o1, we have the whole term equal to big OP since the second part is little o1, we know this is little op. In summary, if kappa max is little o p power minus delta, the perturbation of L is given by little o p power 2 minus 2 delta. Next, we need to find the bound for the eigengap. Which is suppression D and 0, and also it's equal to the minimum eigenvalue of matrix. Let's define some notation first. This matrix WF is a column combination, which means we put column together of different matrix to form a big matrix. So for first one, it belongs to R by RK0. And the second is R by K0 times P. So we can rewrite the diagonal matrix D as following. Previously, we know that diagonal matrix D is summation of K0 positive semi-definite matrix. Here, I use this notation to stand for the summation of the matrices. This notation means that so if we multiply these matrices and these huge matrices, here the number of Q transpose is K0. The multiple of these two give the summation. And also recall previously we find the sample covariance matrix for the population covariance matrix in the independent case. We always have this formula. Suppose xi is IID normal 0, 1, normal 0 sigma. Then the sample estimate of sigma is given by this. And we can rewrite in this summation to the matrix form. Which we can define new matrix X, which corresponds to this. So based on this first and the second point, we can write D as something times its transpose. Let's continue to find the minimum eigenvalue. Since we assume R is of rank R, the rank for the matrix L is rank R. Here, sigma R stand for the R's singular value, because for any matrix, for example, M multiple M transpose, the R's singular value for M equal to square root of lambda R of its square version. Next, we apply a useful inequality called will inequality. We can get the will inequality said for matrix A and B, we have following. This inequality is very useful. If you want to learn more about this, you can search minimize characterization of eigenvalue for matrix in the Google. You can directly find the relative result. Let's continue in next page. The reason why we drop this term because it is a matrix satisfies the property that its transpose times itself equal to identity, a kind of a unitary invariant property. Let's look at the second term. Because for positive semi-definite matrix, the largest eigenvalue equals the largest singular value. Inequality here, we use that largest singular value less or equal to kappa max, which is our assumption. And we know the kappa max is of order little o p power minus delta. So this is also little o p power 1 minus delta. For first part, This is of order p power 1 minus delta, since we have shown that in lemma 2, so for this equality, we basically have a term of order 1 p power 1 minus delta minus the little o of p power 1 minus delta. So we have large equal sign. Sorry. So this term is of order p1 minus delta, since this will go to 0. Combined with previous page, we know that minimum eigenvalue of D is we copy based on this inequality sign. We know p power 2 minus 2 delta is big O of the minimum eigenvalue for D, which is also big O of suppression. Under the condition that we have weak cross dependence between latent factor process and vector noise, we have shown that is little o of probability p power 2 minus 2 delta. Also, we show in the previous page that p power 2 minus 2 delta is of big O of suppression. So combine these two, we know this is also little o probability of suppression. Hence, we have the perturbation for L less or equal to 1 over 5. Suppression with high probability because this little o. Or we can see for sufficiently large we can guarantee that less or equal to Now we can apply lemma 1. There exists a matrix P such that and this is the submatrix of perturbation. So we can further enlarge this term. Which is and Q is estimated by the estimator, which is given by formula. Where B is orthogonal complement of Q. Then we can analyze the rate of convergence in L2 norm. The trick here is that we can rewrite Q as Q multiple a matrix and multiple the inverse of that matrix. Then we have a common term for both. Which can be rewritten as following. Here, we use several property of matrix Q and B because they are part of unitary matrix. We use first unitary invariant property, and next we noted that for this matrix, is summation of two positive semi-definite matrix. So the all singular value or eigenvalue for this matrix is large or equal to 1. So if we take the inverse, all the eigenvalue is less or equal to 1. And it can be further upper bound by the reason is that suppose we have SVD for P, where this matrix is diagonal. This matrix can be written as following eigenvalue decomposition. Since we have the basic inequality, that's why we get this. Because we already show that perturbation, the operator norm of P is upper bound by so the perturbation of Q here we use the fact that which is shown in this right corner. And second is this bond. So we got that if we have weak cross dependence. Next, let's show the second scenario, which is strong cross dependence. Assumption for this case is that the factor strings of little o of minimal singular value of autocovariance between the latent vector process and white noise. Basically, we can go through the similar idea. First, we apply the Weil inequality. We can get which is equal to let's copy this to the next page. For the first term, similar argument, we got this. And the second term, which is lemma 2, that is of order p power 1 minus delta. Since we assume that p power 1 minus delta is of little o order of kappa mean, then this is kappa mean up to some constant. So we got kappa mean square is big O of suppression. On the second scenario, we recall the perturbation for L is since we have different assumptions, we need to analyze in different way. Notice that this is little o of kappa mean, and this is little o1. So the second term dominates first term. We have little o probability kappa mean. Here this is also little o1, which is little o probability suppression. So we have the condition holds with high probability. Then we can apply the lemma 1 and follow the exact same step. We got the perturbation for Q in L2 norm less equal to 2 times operator norm for P, which is denominator is kappa mean square, since the kappa mean square is less or equal to suppression up to some constant. And the numerator since this is little o, this is little o, still the second term dominate first term. We have which is the second result for the theorem 1. Up to now, we have proved the theorem 1. The rate here can be improved if we have some standard assumption on the white noise. For example, if it is Gaussian, then the rate of convergence is expected to be better. In paper, we consider the sub-Gaussian assumption, which is given by for each entry of epsilon IID for different time and different entry, and the variance of it is equal to some number which is finite. The odd moment is 0, and the even moment is less or equal to some number times k power k. This number is related to the parameter for sub-Gaussian. Because we can define sub-Gaussian in this way. And we know this is less or equal to tau, which is finite. It coincides with the definition of sub-Gaussian. under this extra assumption H, we see the theorem 2. The condition is theorem 1 is same with theorem 1 plus the extra H. And we'll need to assume p power delta over 2 over square root n is little o1. And the dimension is larger than sample size n for this theorem. We still have two scenarios, weak and strong cross-dependence between the latent factor process and error. Compare with theorem 1, we see that the rate is improved by a factor p power delta over 2. We give the proof for this theorem. We have the new assumption on the epsilon t, and this assumption will affect the rate of convergence for this term. Previously, the rate of convergence for this term is given by this number. And if we can show that can be improved to this sharper rate, then the perturbation bound for autocurrence for Y is changed to be since this is little o1, the overall rate is big OP which is improved by a factor of p power delta over 2. Because the previous rate for this is given by and then the perturbation for L is changed to be this term. Here I threw away the first term because by assumption and a similar modification, we know that the first rate is dominated by second because there is a little O1 inside. For other step, they are identically same, so we can get we have proved the theorem 2 under the rate for sample version of autocurrence of epsilon is of order p over n. So it remains to show this rate. Let's define some notation first. Still, we put some column vector together to get a matrix. And this is a column vector of 1. Then we know that average The reason why I write these two terms is because it can bring some convenience for our further analysis, since this three term is asymptotically equivalent So for the sample version, which is given by here I use the similar idea to write the summation of n minus k term to a matrix computation. And because these three terms are asymptotically equivalent, they are very close to each other. So we can write the sample version of autocurrence for epsilon by replacing the n minus k by n and replace the average by the average which given by n minus k number. This change will not affect our rate of convergence because you can directly calculate the rate of convergence and find the first line and the second line. They give the rate of convergence just up to some constant. Let's go to next page. After we do that change, we can rewrite as the equation to the multiple of three matrices. And the matrix in the medium is an idempotent matrix. That is to say, multiple product of this matrix still itself. Now we use the submultiplicity of matrix product. The inequality here is that this idempotent matrix Tj, we look at its structure is identity matrix minus a positive semi-definite matrix. So the all singular value for this matrix is less than 1. So it upper bound by 1. By symmetry, we can only keep one term because another term are exactly the same. Notice that the expectation of this matrix is identity matrix because the IID assumption. So we further rewrite it as following. The reason why we write in this way is because we observe that this is the concentration. Perhaps we can use some standard result for the concentration inequality and get the rate for this term. The trick here is called the matrix entropy. Also, we call it discretization trick. Here, I will give a different proof rather than the proof in the paper. The idea is discretization. Let's introduce the sigma hat to ease the notation. We are going to bound the concentration. Here, by definition of operator norm, as well as the property that sigma hat and identity matrix are symmetric, we can use a variational representation of the operator norm, which is given by notice that there is a maximum. The standard trick to deal with the maximum of something is to use the union bound. However, here, our space is of infinite dimension, so we cannot union bound of infinite things. So we need to do the discretization first. Let's rewrite this space which we are going to take the union bound on this. It is a surface on the p dimension. Let's introduce the discretization trick, which is called epsilon cover. Let M vector belong to this space be the epsilon cover of this space. That it means for any point in this space, there exists the I in the indices 1 to n such that the distance between these 2 points is less or equal to epsilon. If we draw the picture, it's like the union of ball which cover this space. Then we analyze this term. We minus the Vj and added Vj's back. Use triangle inequality. It can be still upper bound by the definition of the epsilon cover. If we take the maximum, it further be upper bounded by then we can take the maximum over a sphere on both sides. we can get Notice that the left-hand side is just the definition of the operator norm. Then, after some arrangement, we got the operator norm is upper bound by Then, let's consider the tail probability. Which is the key step to find the upper bound, high probability upper bound. By the above inequality, and apply the union bound. For this term, we can pick the specific value of epsilon, then it can be a constant, which is bound away from 0. Let's go back to the original definition of sigma hat minus the identity matrix. We call the 1 minus epsilon square minus 2 epsilon as constant C1. Since the n minus k is no different or different with the n just by a constant, we can change this to n. We rewrite this term as the following term for purpose. The reason why we write in this way is because now we have the quadratic form for the random vector. And each entry of the random vector satisfies the sub-Gaussian condition. Then there is a very powerful and useful inequality called Hansen-Wright inequality, which can deal with quadratic form and sub-Gaussian case specifically. Let's write down that lemma without proof. The description of lemma goes in following way. Suppose we have a random vector, and each entry IID with mean 0. And also sub-Gaussian condition. For some positive constant k, then for matrix of size n by n, we have following inequality. The quadratic form concentrates to its mean. Which has exponential decay for the tail probability. Notice that we need to change this to the format like this. Let's do this transformation. Use similar idea we have used before. We put the vector together to form a big vector and also form a big matrix. This vector is 1 by Pn. This matrix is Pn by Pn. And this vector is Pn by 1. And a very simple exercise tells us here this matrix is, we call it A. It has Frobenius norm n and operator norm 1. You can verify this easily by the singular value decomposition. So the tail probability is given by after we get the tail probability, we need to get the number of this tail probability we want to sum up. That is the total number in the union bound. So the question is, how large is M? Here, I do not show it, but you can search in the Google covering and packing number, which is a very standard result. We can take, for example, epsilon equal to 1 minus 4, and then M can be taken to be 9 to power P. Plug in the value of epsilon and M. We got that is to say, this is upper bound by this rate up to some constant with high probability. Since in our assumption we have the dimension is larger, then the second term in the rate dominates its square root version. Then we have the rate P over N with high probability. That is to say, equal to big OP 1 plus P over N, and use the assumption N equal to big OP again. We know the 1 can be dominated by P over N. So we prove the rate P over N as we want. The theorem 2 is done. Next, let's talk about the final theorem in the paper, which assume the eigenvalue for the covariance matrix of white noise is uniform bounded when p and n goes to infinity. For theorem 3, we want to get the prediction error bound. And since we already know the parameter error bound in previous theorem, the prediction error bound is straightforward. Let's do it. We replace yt by our model setting. We call this three term K1, K2, K3, and we analyze these three one by one. For the perturbation of eigenspace, we can immediately get it bound since by following trick minus and add Simpsons. Which we further use unitary invariant property and triangle inequality. And for K2 term, since for this, we show in the theorem 1 and 2, it has order little o1. Then we can ignore this K2 term. The prediction bound is given by here we remove the K2 term. For this ft, in the lemma 3, we show it has order p power 1 minus delta over 2. And for the second part, Q transpose the error. We expand it. And triangle inequality. By our assumption, the mean for the error is 0. So the mean for the eigenvector transpose the error is also 0. And the variance for this term, by our assumption that maximum eigenvalue of covariance for sigma epsilon is bounded, we know the variance for this term, which is less than the maximum eigenvalue, is also bounded. That is to say, for this random variable, it has mean 0 and finite variance. So it has order 1, which is very easy exercise. Then we get is also have order 1 because R is fixed constant. Combine these two rates, the perturbation error is of order then we standardize by the factor square root p. We have a standardized error, which is of rate This completes the proof for theorem 3. That's all for the proof in this paper.